I would like to invite our Vice President and Vice Chancellor of Research and also Chair Professor in Logistics and Supply Chain Management, Professor Max Shan, to give a welcome speech. Thank you, Professor Max Shan.
Okay, thank you, Yunhong. Good morning, David. Good evening, good afternoon, or good morning to all seminar participants, depending on where you are. It's my great pleasure to welcome all of you to join our Systems Analytics Global Leaders Seminars. It's organized by the Department of Industrial and Manufacturing System Engineering at University of Hong Kong. Actually, today is a special day in Hong Kong since we have been experiencing number 8 storm signal most of the day. So what that means, number 8, it means the winds with mean speed of 63 kilometers per hour or more has been blowing all day. And the winds has brought heavy rains to Hong Kong too. So actually we've been working from home all day. And we've been looking forward to this exciting seminar all day too, because it's been quite boring look at the rain all day. So today we are really honored to have Professor David Simchi-Levi from MIT to share with us some of his most recent research. I'm sure most of you, if not all of you, owns a copy of some of David's most influential books on supply chain management. I have known David for a long time, actually to be 25 years to be exact. He brought me into the world of supply chain management when I started my PhD journey with him at Northwestern. And he has been a great mentor and friend to me all these 25 years. But most importantly, he has been a very productive leading researcher in our fields, making contributions in many research areas. Even to date, I have to keep up with him to learn from him, otherwise I'll be obsolete. So today, all of us will have a chance to learn from him some of his most recent research on statistical learning in operations. So I would like to take this opportunity to thank the organizing team for inviting David and making sure the seminar goes smoothly. And I also want to thank all of you for attending the seminar today. Now let my department chair, Professor George Huang, to give a more detailed introduction of David. Thank you. George?
Thank you so much, Max, for the introduction. I think I will pass this to Yonghong to give the introduction. But thank you, David, for your time. And I will pass this to Yonghong. Yonghong, please.
Okay, yeah, thank you, Professor Max Shan, and thank you, Professor George Huang. So I would like to introduce Professor David Simchi-Levi to all of you. I think all of you know the very distinguished accomplishment by Professor David Simchi-Levi, but so we will do this introduction. Professor Simchi-Levi is a professor of engineering systems at MIT and serves as the head of MIT Data Science Lab. He is considered one of the premier thought leaders in supply chain management and business analytics. His PhD students have accepted faculty positions in leading academic institutes, including UC Berkeley, Carnegie Mellon University, Columbia, Duke, Georgia Tech, Harvard, UIUC, University of Michigan, Purdue, Virginia Tech. Professor Simchi-Levi is current editor-in-chief of Management Science, one of the 2 flagship journals of Informs. He served as editor-in-chief for Operations Research, the other flagship journal of Informs, and also Naval Research Logistics. In 2020, he was awarded the prestigious Informs Impact Prize for playing a leading role in developing and disseminating a new highly impact paradigm for the identification and mitigation of risk in global supply chains. He was the founder of Logic Tools, which provide software solutions and professional services for supply chain optimization, and became part of IBM in 2009. He co-founded OPS Rules, an operations analytics consulting company, and Operalytics, a cloud analytics platform company focusing on operations and supply chain intelligence. Both companies became part of Accenture. Without further ado, I would like to invite Professor David Simchi-Levi to share his recent research with us. Thank you, Professor David Simchi-Levi. Yeah.
Thank you. Welcome, everybody. Good evening, good afternoon, good morning. I would like to thank the organizers for inviting me, including Professor Mac-Chan, Professor George, and Professor Yong Hang. It's really great to be in this environment. I miss, to be direct, I miss visiting Hong Kong and China. I used to come in normal times to your region of the world, maybe 3-4 times a year. There are lots of familiar faces on this Zoom call, including colleagues, collaborators, and former PhD students. So this is really like being in a family gathering with 280 family members. So it's great. If I can share my screen, does this make sense,
Yes.
guys?
Yes, I think yes. Yeah, please.
Okay.
Yeah, please. Yeah.
Okay, so let me share my screen and you will tell me when you can see it, right?
Yes, yes, perfect. Thank you.
Okay, so today I'm going to talk about recent work that my group at MIT has done in statistical learning in operation. In particular, I'll focus on the interplay between what is called in statistical learning, online and offline learning. But before I jump into the research, it will be good to describe the environment at MIT that has led to this work. At MIT, I lead the data science lab. The data science lab is a partnership between MIT and about 25 different companies, focusing on some of the most challenging problems that these companies have by bringing together data, models, and algorithms. The data science lab is cross-industry. We have partners in oil and gas, retail, financial services, airline, industrial equipment, and software companies who have implemented some of our technology. And the data science lab has a global footprint with partners in North America, Europe, Asia including where you are, but also including the Middle East, as well as Latin America. Let me describe at a high level some of the areas of work that the data science lab has focused on. One big area is around supply chain resiliency that we started way before the pandemic. We started this in 2013, 2014, after events like the tsunami in Japan and the flood in Thailand. And our research and MIT technology has been implemented by companies like the Ford Motor Company that has been using our technology now for a period of about 8 years, but in particular during the pandemic. Company like Sigma, which is a food manufacturing company, Schneider Electric, and recently MIT and Accenture signed a contract around this technology to scale the technology developed by MIT, by the lab, and to make sure that companies in a variety of industries are capable of using this technology for improving the resiliency of their supply chain. A second area of work is all around inventory, transportation, and procurement with companies like Home Depot, with Mango, which is a fashion retailer based on Spain. Of course, Accenture, but also Blue Yonder, who has collaborated with us and some of their clients to address important transportation challenges. Supply chain digitization for ABI, InBev, Zalando. Zalando, by the way, is the largest fashion retailer, online fashion retailer in Europe, Accenture, price optimization, both for online retailer like Groupon, or if you're familiar with, like Oolala, but also brick and mortar retailers like Coppel, which is the largest retailer in Mexico, retail chain in Mexico. Companies like Starwood, which is now part of the Marriott, a hotel chain, part of the Marriott. A lot of work on personalized offering, both in insurance and in the airline industry. Let me describe the work here with an example. If you fly today from London to Paris, when you buy your airline ticket, we are not involved. But once you purchase your airline ticket, our system kicks in. Think about what I'm describing. This is the MIT system kicking in and suggesting to customers ancillary product. Ancillary product include priority boarding, car rental, hotel, and the offers that you get may be different than the offers that I get, because the system learns about your preference and give you an offer designed specifically based on what we learn about individual consumers. The same was done in insurance. And finally, a lot of work on resource allocation with IBM. This is still going on. And with Alibaba, this is work that we did about 2-3 years ago. Today, I'm going to build on the research, on the work, on the collaborations that we have had around personalized offering. In this collaboration with airline and insurance companies, we started diving deeply into the detail of statistical learning. And if you look at the area of statistical learning, and I wrote, just as a comment, my first paper referring to this space published in 2013 at MSAM, where I said we need to change our research from problem-driven research to data-driven research. By data-driven research, I mean the combination of statistical learning, stochastic and deterministic optimization, and the like. So when you dive into statistical learning, you realize that there are two major areas in this space. One is online learning, and the second one is offline learning. Let me define and explain each one of these areas of research. In online learning, no data is available at the beginning of the process. Data is generated on the fly according to some unknown model, and the platform needs to make decisions. Let me illustrate this with a detailed example. A customer arrives at a platform. The platform may be the airline platform that will suggest to you ancillary product. The platform may be Amazon platform. The platform may be a healthcare platform. The platform observes the characteristic of the customer, the feature vector of the customer, XT. Based on the feature vector, we optimize our decision. In healthcare, it may be personalized medication. In the airline examples that I described, it will be a specific ancillary product. And in Amazon case, it may be a recommendation of a specific product to the customer. So the platform makes a decision. Then we observe reward. The assumption is the reward is generated by some unknown model, F star. And this reward depends on the feature and the decision that we made. We will refer to F star as the ground truth reward function that unfortunately our platform does not know and need to learn on the fly. The objective is very simple: design an algorithm that will maximize accumulated reward or equivalently achieve low regret. And we define regret as a difference between the accumulated reward achieved by a decision maker who knows the ground truth F star, and the accumulated reward achieved by our algorithm that does not know F star and need to learn on the fly, right? So maximizing accumulated reward is the same as minimizing regret. And I will talk during this presentation about regret, but we understand the relationship between the two. Offline learning is completely different. In offline learning, the assumption is that all the data is available at the beginning of the process, and this data is assumed to be IID. We cannot generate data on the fly, and our objective is to use the available offline data. We will assume we have n data samples. Each data point is a triplet. It includes the feature vector X, the decisions that we made A, and the rewards that we receive R. And in offline learning, we want to design algorithms that will generate a predictive function F hat that somehow will closely approximate the ground truth F star. Or more specifically, our objective is to design algorithms such that with limited amount of data, we will generate a predictive function F hat such that with high probability, the predictive function F hat will have low error compared to the ground truth. The only thing that is not well defined in this objective is error. And so error intuitively is just the average square difference between the estimated value and the actual value. It's defined precisely here, and it's referred to as MSE or as mean square error. So you notice a few differences between online and offline. The biggest one being the objective in offline is all about minimizing the error. The objective in online is all about regret. Another difference is that in offline, the data assumed to be IID. We will talk about the data generated in the online later on. And as we work with the companies that I mentioned earlier, we realize something very powerful. For offline learning, there are very effective algorithms that allow us to identify a predictive function that has a low error. This is not the case for online learning. In online learning, every time we worked with a company, we had to develop a specific algorithm for that company. And so the first questions that we asked was, is it possible to reduce online learning to offline learning? Because if it's possible to reduce online learning to offline learning, I can use all the available technology for offline learning to solve the online learning problems. These the result of this research are described in the paper Bypassing the Monster that is going to, in fact, appear soon in one of Informed Journal. The second line of research in this space that we focus on is also motivated by comments that we receive from our industrial partner, especially the airline industry. Executives in the airline industry that were using our algorithm for personalized offering were impressed by the performance of our online algorithm. But their comment, their observation was, when you start your online algorithm, you start assuming there is no data available, but this is not the case. Said we have a lot of offline data that is available when you start your online learning algorithm. Why don't you combine learning algorithm? And this is what we address in the second line of research, where we answer the following question. Under what condition offline data does not help the online learning? Under what condition does the offline data help the online learning? And when it helps, by how much it allows us to reduce, to improve our regret performance. Today, I am going to focus mostly on the first line of research, reducing online learning to offline learning. I will talk about this paper titled Bypassing the Monster. In this process, I will explain who is the monster and how we can bypass the monster. So here is an outline for my talk. I will start with some motivation and the key research questions, then explain the technical challenges and highlight our contribution. I'll talk a little bit about the algorithms that we developed and implemented, and explain the theoretical performance of the algorithm. Depending on time, I may dive into the proofs, but I'm not sure how much time I will have to talk about the proof itself. And then I want to show you that this algorithm that comes from the theoretical analysis, it has not only interesting theoretical properties, but it's a very powerful with empirical data. So I'll show some computational experiments. And finally, I want to take 15, maybe 20 minutes to talk a little bit about management science, give you an update of where the journal is, and take questions from the audience, either about the research, the data science lab, or the journal management science. All right, so let me start with the detailed motivation of our work and define the research question. A good starting point is to define the general online learning problems that we are focusing on. And the general problem we are focusing on is called in the CS literature the general contextual bandit model. It's very easy to understand. We play capital T rounds. At time little t, we have an arrival. Think about this as a customer arriving to the airline platform or to Amazon platform. When the customer arrives, we observe the feature vector of the customer xt, and the assumption is that this is generated by some unknown distribution d of x. Once we observe the context, we make a decision A, and this decision belongs to a set of discrete choices. For example, in a recommendation system, there are multiple products that we can choose to recommend. In pricing, there are a discrete set of prices that we can choose from. In personalized medication, there are a set of treatments that we can give. Once we make our decision, we observe the reward, and the assumption is that the expected reward condition on the feature vector and the decision is generated by the ground truth f star. We will assume that f star belongs to some general class of function f, right? And our objective is to design an algorithm that will minimize regret. We are not putting any constraint on the class of function big F. The class of function big F can be linear, can be high dimensional linear, can be non-parametric, perhaps regression trees, perhaps neural network. And this is really why we focus on this question. We focus on this question because what we found was that as we are implementing some algorithm for online learning, every time we implemented an algorithm, we were worried about what is the context, the class of function we are focusing on, and we designed an algorithm for that class of function. Now I want to have a generic algorithm. You give me your class of function, I apply the same algorithm that I apply for other classes of function. And I want to make sure that this generic algorithm, general algorithm, is powerful, independent of the class of functions that we are focusing on. So why this problem receives so much attention in the statistics, CS, even economics, and recently OR literature? Because it combines statistical learning and decision making under uncertainty. And really it has two important characteristics. The first is what is called partial feedback or bandit feedback. When a customer arrives and we observe the contact XT, once we make a decision, we know the reward associated with that decision, but we don't know the reward that we will get if we made a different decision. As a result, one needs to think carefully about the trade-off between exploration and exploitation, between learning and earning throughout the process. This is called partial feedback or bandit feedback. The second one, the second characteristic is heterogeneity. The effectiveness of a specific action depends on the feature vector, on the context. But there are huge number of feature vectors to consider, and it's clearly not possible to learn the effectiveness of each action on every feature vector. So the question is there a way to learn across feature? Is there a way to transfer our learning from one feature to other features? For these two reasons, heterogeneity and bandit feedback, this problem received huge amount of attention. The literature on this problem is very dense, with many algorithms from upper confidence bounds to Thompson sampling. By the way, Thompson sampling is probably the oldest algorithm developed for the classical bandit problem, multi-arm bandit, and then extended to the contextual bandit. This algorithm was developed in the early 1930s by a researcher at Yale Medical School for testing the effectiveness of different drugs, and since then received initially, of course, nobody paid any attention to the Thompson sampling, but at the beginning of 2000, companies like Facebook and Google and Microsoft started reporting that this algorithm works very well, and researchers in our field started doing theoretical analysis to explain why Thompson sampling is so effective. Exponential weighting algorithm, oracle-based algorithm, and the list goes on and on and on. One important highlight is that people have applied some of these algorithms for a variety of applications, such as recommendation systems, ride sharing. My former PhD student and myself, Chris Ferreira Johnson and He Wang, apply the algorithm for dynamic pricing for healthcare. And so you see immediately why these type of problems receive significant attention in multiple areas, in computer science, statistics, economics, and in the last 8 years in operation research. This is clearly relevant to operations. I have here 2 examples. They are very intuitive in product recommendation. I'll show you, by the way, data on the impact of our algorithm for product recommendation later on in the computational experiment. Personalized medicine, let me just focus on this. In personalized medicine, we have K different treatment. Patient arrive one after another. When a patient arrives, we observe the characteristic of the patient, demographic, previous diagnosis, what we know about historical medical issues associated with the person. Then we pick a treatment, right, based on what we learn and based on the feature, and we observe the effectiveness of the treatment. And our objective is to learn the efficacy rate on the fly, so that when new patient arrive, we can personalize effectively the medication to each one of them. So the applications, of course, are everywhere. Why this is challenging? Because we are interested in developing a single algorithm that works for any class of function f. Remember, the ground truth f star belongs to the class of function. And there are 2 important challenges. For every general function class f, we want to make sure that we always find the minimum regret. And so this is called a statistical challenge. And we have a computational challenge, which is how do we make sure that whatever algorithm we develop, this algorithm is computationally efficient. And I will define later on exactly what I mean by computationally efficient algorithm. If you look at the literature on online learning, you very quickly conclude that in the current literature, algorithms are either statistically optimal or computationally optimal, but not both. For example, if you look at those of you who are familiar with UCB or Thompson sampling, know that these algorithms are computationally efficient, but they guarantee optimal regret only for special function classes like parametric. On the other hand, exponential weighting, elimination-based algorithm guarantee to find the optimal regret for every function class f, but they are computationally completely inefficient. And so finding something that has both characteristics is really what drives our research. So let me now dive in more specifically to the research question. So suppose we are given a general function class f. If you look for this function class f at offline regression, at offline learning, this area is well studied. We know that given IID offline data, we know how to find a predictor, a predictive function f hat, such that f hat achieve low estimation error. Remember, low MSE, and there are multiple algorithms to do that. And f hat can be efficiently computed, for example, using gradient descent types of technique. So the offline space is well understood. This is not the case for the online space. And so our objective is to see whether we can reduce the general contextual bandit to the offline regression, because if we can do that, then I will borrow all the existing literature from offline learning to solve the online learning. So more specifically, given a function class f and an offline regression, or call, for example, least square regression, or a variation of it, like ridge or lasso, or other regression oracles. What we want to do is to design an algorithm for the online learning, for the contextual bandit, such that this algorithm for the online learning will always achieve the optimal regret when the offline regression attains the minimum estimation error. And this new algorithm for online learning requires no more computation than the offline regression oracle. That's really our objective. This problem has been mentioned many, many times in the CS literature, in the statistical literature, as an open problem. And as we started looking at this problem, I talked to people in the machine learning community. I talked to people in CS, a lot of them, for example, in MIT. And the assumption, the intuition that people had was that it's impossible to do that. That is, it's not possible to reduce offline learning to online learning for the general. It's not possible to reduce online learning to offline learning for the general function class big F. What you will see is that we answer this challenge in the affirmative. We saw an extremely simple algorithm that achieves that objective. For any function class big F, we can reduce online to offline and therefore use whatever is available for offline to solve the online learning, basically addressing this open problem. And the beauty of this research, and there are lots of people here from our community that are using, I know many of you, that are using CS and machine learning problems, machine learning technique to solve our problem. In the last 10 years, a lot of people have focused on the following approach. Here is an operational problem. The operational problem may be a supply chain problem, maybe an assortment problem, maybe a pricing problem. And they show how they can combine CS technique, machine learning algorithm, with maybe some optimization technology to solve the operational problem. So basically, we are using CS technology to solve the operational problem. In this research, we do the reverse. We use OR technique to solve the CS problem. So remember, what is the CS problem? CS problem is the open problem that I mentioned here. What I am going to do, I am going to use duality theory to solve the CS problem that is described here. And by using the OR technology, you can see that we address the problem that exists in the literature. So let me give us a little bit more insight about why this problem is challenging. And in fact, there are two challenges associated with statistical question. One is related to confidence bound, and the other one is related to analyzing dependent action. Let me start with statistical difficulties that are associated with confidence bound. If you look at algorithms like UCB and Thompson sampling, they work very well for under the assumption that the class big F assumes certain parametric structure. And the reason they work very well is because we can build, in both cases, effective confidence intervals for every pair of context and decision, right? That's the key. For every pair of context and decision, we have the ability to build effective confidence bound. We know from statistics, this is not possible for general function class F. And indeed, in 2018, Foster and his co-authors developed a computationally efficient confidence-bound algorithm that uses offline regression oracle. So they are doing exactly what we are trying to do, But because they are focusing on confidence, efficient confidence bound, their algorithm works only for certain function classes. It does not work in general. The second challenge is a statistical challenge associated with analyzing dependent action. Remember that the offline learning assumes that the data is completely IID, but the data in the online learning is nothing but IID. My decision today depend on all the decision and all the observation I have made up to the current decision. So the IID assumption does not hold at all. And indeed, in a recent paper by Dylan Foster and Sasha Racklin, Sasha is a professor at MIT, actually in the same institute where I am. Dylan Foster was his postdoc. He now is a research scientist at Microsoft Research. They develop an optimal and efficient algorithm for the general problem, but assuming access to online regression oracle. The beauty of online regression oracle, it provides statistical guarantees for any data sequence. So, for example, data that is generated by an adversary. So you don't need the assumption of IID. That's great. The problem is that computationally efficient algorithm for the online regression oracle exists only for special function classes. So from a statistical point of view, this is great. From computational point of view, this is not addressing the problem because we only have online regression oracle algorithm that are efficient for special cases. So here is our contribution. We developed the very first optimal and effective black box reduction from the general online contextual bandit to offline regression. We built on previous research. We borrow an idea from an old paper by Abe and Long. Abe and Long focus on linear bandit problems. And they develop a sampling algorithm to address these problems. Their algorithm works only in special cases of the linear bandit problem. In fact, Sasha and Dylan use this idea when they develop their algorithms that I described in the previous slide, but they require online regression algorithm. There is another line of research by Agrawal and his co-author that works not on the function class space, but on the policy space. These lines of research always were assumed to be completely independent. Basically, in our research, we show that there is a tight relationship between the two, and we can combine them to solve the online regression challenge. The bottom line from our research is that any advances in offline regression immediately translate to the contextual bandit, both statistically and computationally. And that's really a powerful statement. If you are able to come up with an effective algorithm for offline learning, we know how to use it for the seemingly different problem, the online learning problem. Now, to put our contribution in perspective, let me just review some of the existing algorithms for the contextual bandit. One of the first algorithm is regression elimination algorithm by Agrawal in 2012. It guarantees to find the optimal regret, but it's intractable. 2 years later, Agrawal and his co-author developed another algorithm that again guaranteed to find the optimal regret by making this many calls to offline classification oracle. The problem is offline classification oracle, you need to solve NP-hard problems. So computationally, this is not effective. RegCB was developed by Foster. This is the algorithm from 2018 that I described earlier. Require polynomial number of call to offline regression. This is what we are trying to do, but it's suboptimal. It guarantees optimal regret only in special cases. SquareCB is the one developed by Dylan Foster and Sasha Racklin, guarantees to find the optimal regret by making this many call to online regression oracle. The problem is that effective algorithm for the required online regression oracle exists only in special cases. Our algorithm, we call it Falcon. I'll explain the acronym in a second. Always find the optimal regret by making log T calls to offline regression oracle when T is unknown in advance. If T is known in advance, meaning how many customers will arrive, like in drug testing, if T is known in advance, we can reduce the number of calls to the offline regression. But the key is the computational complexity of our algorithm is equivalent to that of solving a few times the offline regression problem. Now, remember, we call our paper bypassing the monster. So you may wonder what monster refers to. In the CS literature, monster refers to algorithms that require a huge amount of computation. And the first to refer to their paper as the monster paper were the authors of this paper, where they develop an algorithm that always find the optimal regret, but as they say, it requires monster amount of computation, and that's why they call their paper the monster paper. In 2014, Agrawal and his co-author developed, in fact, a simple algorithm that always finds the optimal regret, but it requires using calling to offline classification oracle. This implies that you need to solve many times NPR problem. That's why they refer to their paper as tamming the monster. Our approach is completely to bypass the monster just by assuming any general class of function f, big F. All right, so what is the algorithm that we have developed? The algorithm that we developed has 3 components. We start by dividing the planning horizon into sub-intervals of growing length. As we divide into sub-interval, you will see that the length of the sub-intervals is growing. At the beginning of every sub-interval, at the beginning of every epoch, we make one call to the offline regression oracle to obtain our predictor. Okay, so we divide the time horizon into sub-interval. At the beginning of every sub-interval, we make a single call to the offline regression oracle to obtain the predictor f hat. But we are not using the predictor f hat in a greedy fashion. We will use a randomized algorithm, a sampling rule, to make our decision. Our randomized algorithm, the initial idea for the randomized algorithm, as I mentioned, come from Abe and Long, and then later on was used by Foster and Racklin. We call the algorithm Falcon for fast least square regression oracle for contextual bandit, and you can see immediately why we use this name. So let me explain each one of the components of the algorithm. The first is generating an epoch schedule by dividing the time horizon into sub-interval such that the length of each sub-interval is growing. If we don't know T at the beginning of the planning horizon, we just use a geometric sequence, which implies that we will have log T sub-intervals. If we know T in advance, we can reduce the number of sub-intervals to log of T, right? Anyway, when you look at this epoch schedule, you very quickly conclude that the length of each subinterval is going as you move from left to right along the time horizon. This implies that the oracle, the regression oracle, is called less frequently as the algorithm proceeds. The second component is the oracle call. At the beginning of every subinterval or every epoch, we make one call to the offline regression oracle to obtain a predictor f hat. If we want, we can replace the least square oracle by other regression oracle like ridge or lasso, or maybe more sophisticated ones. But the question is, once we have the predictor f hat, what do we do with that? If we directly follow the predictor, it means that we choose a greedy action, then we may have a large regret because the predictor may be off, may not represent the ground truth. And as a result, we are going to use a randomized algorithm to find the right balance between exploration and exploitation. The key innovation in this algorithm is the combination of the three steps, but in particular, the third step. So what do we do in our randomized algorithm? At the beginning of epoch M, we calculate a learning rate. Notice that the learning rate is proportional to the epoch schedule. And so this tells you that as we move from epoch to epoch, the learning rate is increasing. At the beginning of round T, when we are at epoch M, we observe the context, the feature of customer T, right? Here it is. This is what we know about the current customer. We already, at the beginning of epoch M, generated our predictive function f hat, right? And so we know the context, we know the predictive function. Given this, we know a hat, which is the greedy action. If f hat was true, a hat is the best decision. But of course, we don't know that f hat is correct. But if the predictive function is correct, a hat would be the best action to take. Because we don't know if the predictive function correctly represents the ground truth, we are going to use the randomized algorithm described here. We will choose an action A, not the greedy action. We'll choose action A, not the greedy action, with probability inversely proportional to the difference between the predictive function at the greedy action, the value of the predictive function at the greedy action, and the value of the predictive function at action A. The bigger the gap, the smaller the probability. So you can think about this as exploration step. And with the remaining probability, we will select the greedy action. So think about this as the exploitation step. Notice that what control the exploration trade-off is the learning rate gamma, right? As we move from epoch to epoch, the learning rate increases, which implies that we reduce the probability of selecting the non-greedy action. And this is intuitive. As we learn more and more, we are feeling more and more confident about the predictive function f hat. That's the entire algorithm. And you can see that this algorithm can be applied no matter what the function class big F is. What can we say about the performance of our algorithm? Here it is. Suppose big F represents just a finite function class. We show that our algorithm guarantees an expected regret no more than a constant times square root of k times t times log of f, using log t call to a least square regression oracle. If t is unknown in advance, if t is known, we can reduce the number of calls. The beauty of this result is that there is a matching lower bound, which implies that in this case, our algorithm guarantees the optimal regret. Now you may say, hey, finite function class is just a very specialized case. What about the general function class? So let's prepare the setting. Given NIID samples, right, and an offline regression oracle that return a predictor f hat, such that the estimation error is bounded by ER. So think about ER as the estimation error guarantee. And of course, the estimation error guarantee depends on how many samples, the sample size, how many data points you have, and the complexity of the function class F. Given this, here is what we show. Given an offline regression oracle with an estimation error ER, our algorithm guarantees an expected regret no more than square root of K times ER times T. And again, using log T calls when you don't know T. The beauty of this result is if in the offline space, the offline regression oracle generates the minimum possible estimation error value, meaning it finds the rate optimal ER. When the offline regression oracle finds the optimal estimation error, there is a matching lower bound suggesting that our algorithm finds the optimal regret in this case. That is to say, whenever the offline regression oracle returns the rate optimal estimation error guarantee, our algorithm returns the optimal regret. And that's really a powerful statement. As powerful as the offline regression oracle is, that will be the power of the online regression oracle. And we can immediately apply this result to a few open problems. For example, when f is linear with dimension d, we know that least square guarantees an error proportional to d over n. Our algorithm therefore returns a regret proportional to square root of kt d plus log t, which improves on the best known result as a function of t. When f is linear with sparsity s, we know that lasso guarantees an error or proportional to s log d divided by n. Therefore, our algorithm returns a regret proportional to square root of k s t log d in this case. The result work for neural network, the result work for generalized linear, the result work for non-parametric. For example, this tells us immediately what we will have as a regret when the function class f is a neural network. We know when the function class is neural network that the estimation error guarantee is 1 over square root n. As a result, our algorithm returns a regret proportional to t to the power of 3 over 4. And so these are direct corollaries from our analysis. I'm not going to present the proof because this is a little bit too detailed. I want to skip straight to a few observations. The first observation is that sometimes people do not focus in offline regression on mean square errors. They may focus on strongly convex loss function. Our algorithm generalizes, and our result generalizes to this case. It will be interesting to compare our algorithm to square CB, the one by Foster and Racklin that require online regression oracle. So one advantage a square CB has is because they focus on online regression, it allows to consider general context where we assume IID context. The difficulty with square CB is that we have effective algorithm only for special function classes where our algorithm is general, and there are many effective offline regression oracle for available to users. And more importantly, Square CB requires updating the predictive function after every arrival. So this is not effective when there are delays in the reward, like in healthcare. You give the treatment and you need to wait 10 days until you observe the impact of the treatment. Our algorithm, remember, allows you to wait until the end of the epoch when you update the predictive function. So this brings me to talk about computational experiment. And I want to show that this algorithm that comes from theory and has some beautiful theoretical properties is in fact powerful with real-world data. And here I'm going to describe a computational experiment with 3 classes of data sets: classification data or classification problems, recommendation problems, and price optimization problems. Let me start with classification and recommendation data sets. We use 10 classification data sets and 2 recommendation data sets from open source data sets. You can see here Microsoft and Yahoo public data. Classification, for those who don't know, classification is a fundamental problem, fundamental task in machine learning. In online classification, people use this type of technology for identifying handwriting, for face recognition, for a segmentation to identify customer groups that a new customer belongs to. For promotion design, the application area is enormous. In the data sets, when the algorithm classifies a customer correctly, then we have a 0 loss. When we make any mistake, it doesn't matter how big or small the mistake is, then the loss is 1. Recommendation systems are used, of course, to predict the ranking or the rating that a user will give a product when a customer arrives. If we recommend a product that the customer likes the most, then we have a smaller loss. If we recommend a product that she ranked low, then we have a larger loss. And these recommendation systems are used by Amazon, Netflix, Google, so they are everywhere. And that's why there is a rich data set that we can choose from. We compare the performance of Falcon, our algorithm, to the performance of 8 different algorithms that all exist on open source library called VW. This was done about 8 months ago, so the version, or 10 months ago, the version that we use of the existing algorithm is version 8.8. The algorithms that we compete with include greedy, just use a greedy action based on the predictor that you have. Epsilon greedy, in philosophy, it's similar to our algorithm. With certain probability, you select the greedy action, and with uniform, you select from all the other actions. And then we took 2 versions from Taming the Monster. We took 2 versions from Thompson sampling. And the best algorithm up to our test were associated with RegCB. There are 2 versions of RegCB, elimination and optimistic. We tested across both of them. This RegCB, just as a comment, was developed by Foster and his co-author in the paper from 2018 that I mentioned earlier. It's very powerful empirically, but as I mentioned, it's suboptimal. It doesn't guarantee to generate the optimal regret. So I'm going to compare the different algorithms using what is called in the CS literature win-loss difference. So forget about our algorithm. For now, there are 8 existing algorithms that we are testing. And I want to compare every algorithm in this list of 8 algorithms against every other algorithm on the set of 12 data sets. So for example, in this table, you can see I am comparing back greedy to greedy. So on the 12 data sets, suppose that back greedy statistically was more effective than greedy in 6 cases. Suppose that greedy was statistically more effective than back greedy on 2, and on the other, we cannot say which one is better statistically better. And so we record here 6 minus 2 or 4, right? And you can see the win-loss difference in this table for all the existing algorithms. RegCB are the best. This was reported by others. This is reported by us. In fact, RegCB optimistic never loses to anybody. Now we tested also our algorithm, and we tested 3 versions of our algorithm. And the reason I can test 3 versions of our algorithm because it's so general. So Falcon 1 assume linear class and apply least square estimator as the offline oracle. Falcon 2 assume linear class and apply ridge estimator, and Falcon 3 assume general class, for example, regression tree, and apply gradient boosting. And you can see that our algorithm in general perform very well, but Falcon 3 is a more general algorithm that assume regression tree and apply gradient boosting, never loses to anybody, basically dominates this table. And so the third test that we performed was a test associated with dynamic pricing. We received data from Columbia University Center of Pricing and Revenue Management. This data represent 200,000 auto loans, application over a period of about 4 months. Each application is characterized by more than 100 features. Like many other papers, we selected the 5 most important features. You can see them here. And we tested 2 settings. One, when the price range is between $500 and $7,500, and we discretize to 15 price choices. The other one is the range is between 1,000 and 10,000, and in setting 2 there are 10 price choices, and we can apply the different algorithm, and you can see the same performance as before. Here is the performance of all the 8 algorithms in terms of average revenue. Here is Falcon. For Falcon, we assume linear function class, and immediately some of you are asking, why linear? But we assume linear function class and linear least square regression oracle. You can see Falcon does very well, outperform everybody. But the questions that come to mind when you look at revenue, why are you assuming linear function class? Revenue is not linear as a function of price. And so we also tested 3 versions: linear with least square, linear with ridge, and general function class regression T with gradient boosting. And you can see gradient boosting is doing the best. The beauty of this is that it's very general, therefore allow the decision maker to decide which function class is appropriate. Let me just conclude by saying that bypassing the monster was accepted just recently in Math of OR. We recently extended the result. The result that I describe here are focused on min-max regret. We extended the result together with Dylan Foster and Sasha Racklin to instance-dependent regret as well as reinforcement learning. This was accepted and appeared in a very prestigious CS conference called of this year. I should also point out that what rewarding in our business is when other people look at your paper and say, hey, this is a great idea, let's extend what these people have done. And since our paper was posted in archive, many follow-up papers appear. People from Columbia University extended our result to infinite action. People from Stanford extended our result when F is misspecified. People from USC extended our result to non-stationary. People from Amazon extended our result to contextual, and the list is long and is growing. And so this concludes the first part of my talk, which is the talk about research. I want now to take you through a quick update on management science, and then open it to any comments and discussion. Yonghong, is this appropriate, or you want to take question now?
I think it's good. You can talk about management science first, because I think so audience. So if you have questions, so you may use the Q&A box. So then we collect the questions. Then we can ask you the questions after the journal.
Okay.
Thank you.
Oh. Yeah. All right. So here is an update on management science. Management science is the largest by far journal of informs. You can see here year by year submission for the first 3 quarters of the year. In this year, 2021, in the first 3 quarters, we received almost 3,300 papers. You can see that we will increase dramatically this year submission volume relative to last year. I estimate, based on what we have seen so far, that we will get about 44,000 plus papers this year. Our acceptance rate is about 10.5%, but it varies between fast track and regular. You know that in 2018, we introduced a new submission channel called fast track, which highlights shorter paper, different writing styles. A regular paper acceptance rate is about 11%. Fast track paper acceptance rate is about 7%. What about usage? Usage means how many downloads we see of papers published in management science. Again, by far, this is the largest among all informs journal. And finally, authors benefit from really a short response time. If you think about time from submission to first decision, the average time this year was about 80 days. If I look at the same statistic, by the way, for fast track papers, you are talking for fast track at about 30 days. That's unbelievable response time. If you look at time from submission to final decisions, the median is 90 days. Compare this to, say, 2018. We cut the time from submission to final decision dramatically for management science. Maybe something you don't know is Google Scholar metrics of all academic scientific journals. So what I did with the help of some people is to look at Google Scholar metrics for all 24 journals on University of Texas Dallas list, and you can see all of them here. What Google Scholar metrics provide is what they call H5 index and H5 median. What are these metrics? These account for citations of papers published in each one of the journals. This is citation of paper published in each one of the journal for in the last 5 years, in the last 5 completed years, you can see that management science is in the top 4. In the top 4, the other journals are finance journals. And I want you to remember this statistic. I talk and I visit a lot of business schools, and when I talk to finance faculty in some universities, they say, you know, we recognize management science is a quality journal, but it's not the same quality as finance journal. This is not the case. Look at here. We, management science, occupy basically the same space as the top finance journal. You can also see that we are doing extremely well relative to other informed journals. I used to be the editor-in-chief of Operation Research. You can see it here. I used to be the editor-in-chief of Naval Research. It's not counted. You can see here POMS. You can see here other journals in our profession. Before I open it for comments, let me just highlight a couple of initiatives. We implemented data and code disclosure policy at in the middle of 2019, and I appointed a data editor that helped facilitate the process at the beginning of last year. We are engaging in replication project. If you're doing behavioral operations, you may be interested in the replication project. There is a website that where you can get a lot of information about the replication project. There are about 10 faculty from 5 universities involved in the replication project. The faculty involved surveyed the community and selected 10 papers that they are replicating. They are now in the process. If you want to learn more, go to the management science website and click on the replication project. You can learn more about that. Just a couple of comments about special issues. All of them that you see here are special issues that were introduced before, and in a second I'll talk about a new special issue. 65th anniversary special issue was just published last month. Data-driven perspective received more than 200 submissions and will be published this year. Business and climate change special issue received almost 250, and blockchain crypto economic received more than 100. Each one of the special issues, by the way, I follow the same philosophy of bringing together multiple departments. For example, blockchain and crypto economic bring finance and operation. Data-driven perspective bring data science, operation, marketing, finance, IS. And so there is a new special issue focusing on human algorithm connection. And you can see that we bring in this special issue people from a variety of departments: operation management, finance, behavioral, market design, data science, marketing, and information system. You have plenty of time to submit. The deadline is September of next year, and I'm hoping to see many papers submitted. This is a growing area in our field. It's an important area, not only academically, but even more importantly for business professionals. Let me pause here and see if there are comments or questions, either on research or on management science.
Okay, so thank you very much, Professor Simchi-Levi. So we have a few questions from the Q&A box. So the first question is from Jiang, a PhD student of Dalian University of Technology. So the question was how to guarantee the error of the algorithm. What is the technology behind that?
Yeah, so the error guarantees that we prove was by focusing instead, and that's the step, of course, that I skipped in this presentation. I didn't talk about the proof, but the error guarantee, the regret guarantee that we provide was by looking instead of the function class, we basically relax the problem and focus on a policy class. And we show that if you focus on the policy class, there is a beautiful way to connect f hat, which is a predictive function, to f star, which is the ground truth. And if you think about our work, our work basically makes this contribution, connecting the ground truth to the predictive function. For the offline, the estimation error guarantee comes with the algorithm. As I mentioned, there are a variety of algorithms that provide, depending on the function class f, estimation error guarantee. We are using that to provide the regret guarantee.
Yeah, thank you very much, Professor Simchi-Levi. So we have a few more questions. One from Derek from Hong Kong U. Thank you for the very insightful talk. So he wonders if there is any assumption on the data, if the patterns of the data change significantly over time, would that affect the performance of the offline learning approach as compared with the online one? Thank you.
Beautiful. So remember, in the offline, the assumption is the data is IID. So if the data is not IID, the offline is not going to work. In the online, the assumption is that the not that the data is IID, of course not, but the assumption in the online is that the context vector is generated from a fixed distribution. As I mentioned, some of the extensions that were done involve situation where the distribution is drifting, where the distribution is non-stationary, and the results that I mentioned from people in computer science at USC show how to adjust to this environment.
Yeah, thank you, Professor Simchi-Levi. So Derek has another question. Are there any assumptions on the number of features or volume of data?
There is no assumption on the number of features. Remember, our result hold for general function class, and the number of arrival is in the regret. So remember, T, which is the number of arrival, is part of our regret guarantee.
Great. Yeah, thank you. The next question from Lee, how can we apply Falcon in a dynamic environment? Thank you. Yeah.
So Falcon is designed for a dynamic environment, because in a dynamic environment, things arrive on the fly. Now, it's possible that the question is not just dynamic, but non-stationary, right? So you need to adjust, of course, the algorithm, and you need also to define what do you mean by non-stationary, right? If non-stationary means that you can be anywhere at any point in time, that will not work. But if there is a budget, meaning you limit how non-stationary the process can be, then the people from USC showed how to adjust our algorithm.
Thank you, Professor Simchi-Levi. The next question is from Li Zitian. Li thinks that the sampling rule is quite clean, but we can use different formulas whose probability decreases the gap of the predicted reward between A and A hat. What is the insight of this formula? So Li,
very nice.
Master, yeah.
This question is really to the heart of the proof.
Yeah.
And the way we are doing this is showing, remember I said we are doing the connection between the ground truth, F star, and the predictive function F hat. In fact, what we are doing is the following. we are looking at, for every epoch, what is the true regret associated with the ground truth. And we are comparing it to imaginary regret. You're asking yourself, what is he talking? What is imaginary regret? Imaginary regret is regret if f hat was true. And we show that we can limit. So let me take you to this. This is a very insightful question, and you can see it in my slide here. And we can show that our sampling rule is the one that allow us to bound this different. And you can see it here. The left-hand side is the true regret associated with f star. In the right-hand side, I have two components. One is imaginary regret if f hat was true, right? So this equation says, aha, the true regret is no more than 2 times the imaginary regret plus something that is decreasing with the learning rate. And that's why we selected very carefully the learning rate. This learning rate is the one that allow us to bound the total regret in our algorithm.
Great. Okay. So I think I also have one question. I know that so actually your talk is very insightful. My question is in the OR community, we have a lot of tools that can contribute to, let's say, solving problems, challenging problems in machine learning, data science. I think Professor Simchi-Levi, you have done a lot of great work in this area. And my question is, as a junior faculty member, in this area of research, let's say we are talking about data science, machine learning, artificial intelligence. So what do you think in the OR community we can contribute the most to solve some challenging problems?
So actually, it's an excellent question. And my there is no crystal ball, just to be clear.
Yeah.
I'm going to talk only on my experience.
Yeah.
My experience is we are different in general than the CS community.
Mm.
In the CS community, when they think about data science, machine learning algorithm, they are not interested in the characteristic of a specific domain.
Mm-hmm.
We are interested in the characteristic of specific domain. When Max Chan is doing research on last mile, on logistics, he may be applying machine learning, but he takes advantage of the characteristic of the problem.
Right.
When we do pricing, we take advantage of the characteristic of the problem. That's what makes a big difference between us and the CS community. I have a student who just recently worked on last mile, and what he does is leveraging flexibility, the characteristic of flexibility, together with machine learning algorithm to achieve better results than either one can do. Does this make sense? That's really the power of what we bring to the table. What I wanted to highlight here is another element, just to be clear. You really open a very big box that allows me to give you my experience. What I want to say is, so that's one area. The second capabilities that we bring is there are lots of interesting, important CS and statistical open problems. Here is one. Another one, you may know my student, some of you may know my student, Jing Long, who worked on switchback experimentation. This is well known in statistics, used by many companies to test a variety of pricing and assortment. What was not known in switchback, what is the optimal design? In both this paper, Bypassing the Monster, and switchback, we take this problem, one is statistical problem, one is a CS problem, and we turn them upside down. Instead of looking at the statistical problem as a problem purely statistic, we basically converted it into a competitive analysis. And we show, oh, when you look at it from the magnifying glasses of competitive analysis, you can find the optimal design. Similarly here, when you relax the problem and focus on a dual interpretation of the problem, all of a sudden, beautiful insight come to the contextual bandit.